Deep in the endless black of space, something strange is happening. Powerful bursts of radio waves, more energy than our sun produces in 80 years, flash across the cosmos in less time than it takes to blink. These aren't signals from any human technology. They're not coming from anything we understand. Fast radio bursts, some of the universe's loudest and most mysterious screams, echo through the darkness. Here's what makes them so terrifying: we don't know if they're the desperate calls of an advanced alien civilization trying to reach out, or the violent death cries of collapsing stars and unraveling galaxies. One thing's certain, these bursts carry secrets that could rewrite everything we know about space. Stick around, because by the time we're done, you'll understand why scientists are racing to solve this cosmic mystery, and why the answer might change how we see our place in the universe forever. Now, let's step back to where it all began. The story of fast radio bursts starts not in some high-tech lab, but in a pile of old data. In 2007, astronomer Duncan Lorimer and his student David Narkevic were sifting through observations from the Parkes Radio Telescope in Australia, recordings that had been quietly sitting around for 6 years. They weren't hunting for anything in particular, just combing through cosmic static-like detectives, reviewing cold case files. Then they saw it, a single spike of energy so intense it made their instruments jump. A burst of radio waves lasting just 5 milliseconds, but packing more power than our sun emits in 80 years. At first, they thought it might be a glitch. Maybe a satellite passed by, or someone nearby turned on a microwave. But when they checked again, the signal was real, and it came from somewhere far beyond our galaxy, over 3 billion light-years away. That's when the realization hit: this wasn't something humans made, or even something natural we'd seen before. It was a cosmic scream from the depths of space, a flicker of energy so brief you'd miss it if you blinked, but so powerful it left scientists speechless. The Parkes telescope, with its giant white dish nestled in the Australian outback, became ground zero for this mystery. Radio telescopes like Parkes work like cosmic ears, picking up whispers from the universe that our eyes can't see. But this wasn't a whisper, it was a shout. The signal was so strong and so fast that it didn't match anything in the known universe. No star, no pulsar, no known cosmic event behaved like this. Here's where things get even wilder. That first burst, now called the Lorimer burst, wasn't just a one-time fluke. Since then, astronomers have spotted hundreds of these fast radio bursts, some repeating like clockwork, others flashing just once and vanishing forever. Each one carries enough energy to power our entire civilization for centuries, but they last less time than it takes for a camera flash to go off. Detecting them is like trying to catch lightning in a bottle. Radio telescopes have to stare at the same patch of sky for days, sometimes years, just waiting for a split-second flicker, and when they do catch one, the data looks like a seismograph during an earthquake, a sharp, jagged line that tells us something massive just happened, but leaves us guessing what. Scientists still argue over what could possibly create such extreme bursts. So why does this matter? Because every time we detect one, it's like picking up a message in a bottle from the farthest corners of the universe. Whether they're alien signals or cosmic catastrophes, fast radio bursts are forcing us to rethink what we know about space, and the hunt for answers is just getting started. But here's the catch: fast radio bursts aren't just random blips in the void. They come with a set of bizarre, almost impossible features that make them stand out in the cosmic crowd. Let's peel back the layers of these enigmatic signals and see what makes them so extraordinary. First, their brevity. These bursts are over in the blink of an eye, literally. Lasting just milliseconds, they're gone before our telescopes can even process what they've seen. Imagine trying to study a firework by its afterimage. That's the challenge scientists face, yet in that fleeting moment, they unleash a staggering amount of energy. Some bursts emit more power in 5 milliseconds than our Sun does in 80 years. Packing that much punch into such a tiny window defies everything we know about how energy behaves in space. Then there's the way they travel. Fast radio bursts don't arrive in a clean, sharp signal. Instead, they're stretched out, with lower frequencies arriving slightly later than higher ones. This effect, called dispersion, is like listening to a song where the bass notes drag behind the melody. But here's why it matters. Dispersion is a cosmic breadcrumb. The more stretched out the signal, the farther it's traveled through the ionized gas between galaxies. Some bursts are so dispersed, we know they've crossed billions of light years, making them some of the most distant phenomena we've ever detected. Now, let's talk about the split personality of fast radio bursts. Some are one-hit wonders, flaring once and vanishing without a trace. Others are repeat offenders, firing off multiple bursts from the same patch of sky. The repeaters are especially baffling because they don't follow a schedule. They might go silent for months, then suddenly erupt a dozen times in a week. It's as if whatever's producing them has an on and off switch we can't predict. This irregularity has led to a cosmic detective story. Non-repeating bursts could be the death cries of catastrophic events, neutron stars colliding, black holes forming, or other universe-shaking disasters. But the repeaters, they suggest something more stable, like a spinning magnetar, a highly magnetic neutron star having violent tantrums, or, if you let your imagination run wild, something more engineered. Whatever their origin, one thing's clear: fast radio bursts are rewriting the rules of astrophysics. They're not just dots on a graph. They're messages from the farthest, most hostile corners of the cosmos, and decoding them might just change how we see the universe. But what if these cosmic whispers aren't just random acts of nature? What if they're intentional, a sign that we're not alone? That's the spine-tingling possibility behind the alien hypothesis. Some scientists have dared to ask, could fast radio bursts be the interstellar equivalent of a lighthouse beam, purposefully sweeping across the cosmos? Enter the lighthouse model. Picture an advanced civilization far beyond our technological grasp, using neutron stars as cosmic antennas. These aliens might harness the star's insane magnetic fields to focus and amplify signals, turning them into pulsing beacons. The idea isn't as wild as it sounds. After all, we've used radio waves for communication for over a century. Who's to say a more advanced species wouldn't refine this into something far more powerful? The repeating bursts could be their way of saying, "We're here," while the one-offs might be accidental transmissions, cosmic machinery glitching in the void. Then came the bombshell of 2017. A pair of Harvard astrophysicists suggested that some FRBs might originate near alien megastructures, specifically Dyson spheres. These hypothetical constructs, swarms of solar panels encircling a star to harvest its energy, could leak immense power surges. If a civilization were tinkering with such technology, their experiments might produce the very bursts we're detecting. It's a tantalizing thought. Those spikes of energy could be the byproduct of a society mastering stellar engineering. But let's be clear, this isn't just sci-fi speculation. The math, at least, checks out. The energy required to generate an FRB aligns with what a Dyson sphere might accidentally emit. and the irregular timing of repeaters. That could hint at construction phases or power fluctuations in these megaprojects. Of course, critics argue it's a stretch. The universe is under no obligation to cater to our fantasies of first contact. Yet even the skeptics admit, if we ever do find proof of ET, FRBs might be our first clue. So where does that leave us? For now, the alien hypothesis remains a thrilling what if. But it's a reminder that the cosmos is vast and our imagination is just catching up. Whether these bursts are natural or engineered, one thing's certain: they're pushing us to think bigger, to question not just how the universe works, but who else might be out there, turning the dials. Now, let's step back for a moment and consider the other side of the coin. As thrilling as the alien hypothesis may be, science thrives on skepticism, on questioning even the most captivating ideas. And when it comes to fast radio bursts, many researchers argue that the simplest explanation is often the correct one. This is where Occam's razor comes into play. The principle suggests that among competing theories, the one with the fewest assumptions is usually true. So, while the idea of extraterrestrial engineers behind FRBs sparks the imagination, the scientific community urges caution. Take the lack of repeating patterns, for instance. If these bursts were deliberate signals from an advanced civilization, wouldn't we expect some consistency, a predictable sequence, perhaps even a decipherable message? Yet, most FRBs are chaotic, with no clear structure or repetition beyond the occasional repeater's erratic behavior. Even the famous FRB 121102, which does repeat, shows no discernible pattern that hints at intelligent design. SETI researchers, who spend their careers hunting for extraterrestrial transmissions, point out that real communication attempts would likely be more organized. Then there's the sheer energy involved. While it's true that a Dyson sphere or similar megastructure could theoretically produce such power, the universe is full of naturally occurring phenomena that pack just as much punch. Magnetars, for example, are neutron stars with magnetic fields billions of times stronger than Earth's. These cosmic powerhouses can generate flares so intense they ripple across galaxies, no aliens required. The natural processes behind these events are well documented, making them a far more plausible source for FRBs. Critics also highlight the vast distances these signals travel. If FRBs were engineered, their creators would need to account for the dispersion and distortion caused by interstellar gas and plasma. Yet, the bursts we detect show no signs of being cleaned up or optimized for long-distance communication. Instead, they arrive scrambled by the very medium they've traversed, much like natural cosmic noise. Of course, none of this outright disproves the alien hypothesis. Science leaves room for wonder, and the search for extraterrestrial intelligence continues. But as one SETI scientist put it, extraordinary claims require extraordinary evidence. Until we find a burst that carries an unmistakable signature of artificial origin, like a mathematical sequence or a deliberate repetition, the scales tip toward natural explanations. So, while the idea of FRBs as alien signals is undeniably thrilling, the scientific consensus leans toward cosmic phenomena we're only beginning to understand. And that, in its own way, is just as exciting, because whether these bursts are the work of nature or some distant civilization, they're undeniably rewriting the rules of what we know about the universe. Now, let's turn our attention to one of the most compelling natural explanations for fast radio bursts: neutron stars, specifically their most extreme variant, magnetars. These cosmic powerhouses are not just fascinating in their own right. They might be the key to unlocking the FRB mystery. Neutron stars are the collapsed cores of massive stars that have exploded in supernova, packing more than the Sun's mass into a sphere no wider than a city. They're among the densest objects in the universe, but magnetars take this intensity to another level. With magnetic fields 1,000 trillion times stronger than Earth's, these stars are like cosmic magnets on steroids, and when they act up, the results are nothing short of spectacular. One leading theory suggests that fast radio bursts could be produced by starquakes, violent fractures in a magnetar's rigid crust. Imagine the star's surface cracking under unimaginable stress, releasing pent-up energy in a sudden, catastrophic snap. These quakes ripple through the magnetar's magnetic field, twisting and stretching it until bam, a colossal burst of radio waves erupts into space. It's like the cosmic equivalent of a rubber band snapping, only with enough energy to outshine entire galaxies for a split second. Then there's magnetic reconnection, another prime suspect. This process occurs when tangled magnetic field lines suddenly rearrange themselves, converting magnetic energy into radiation and particle acceleration. On the Sun, we see this in solar flares, but on a magnetar, the scale is mind-bending. A single reconnection event could unleash a firestorm of radio waves powerful enough to travel billions of light years, perfectly matching the profile of an FRB. The evidence supporting this idea is growing. In 2020, astronomers detected an FRB originating from inside our own galaxy, traced back to a known magnetar called SGR 1935 plus 2154. This was a game-changer. For the first time, we had a direct link between a magnetar's outburst and an FRB. The burst itself wasn't as energetic as those from distant galaxies, but the mechanism was unmistakable, a violent flare from a highly magnetized neutron star. What's truly remarkable is how these natural processes can account for both repeating and one-off FRBs. A magnetar might produce multiple bursts if its crust is constantly cracking under strain, or it could unleash a single cataclysmic event that leaves it permanently altered. Either way, the physics fits without invoking alien megastructures. Of course, magnetars aren't the only possible explanation, but they're a prime example of how the universe, in its raw, untamed state, can generate phenomena that seem almost engineered. The deeper we dig into these stellar powerhouses, the more we realize nature, left to its own devices, is plenty capable of producing the extraordinary. But while magnetars offer one compelling explanation, the universe has even more extreme events up its sleeve. Let's venture into the realm of cosmic cataclysms, the kind of violence that reshapes space-time itself, and how these apocalyptic moments might be the true source of some fast radio bursts. Picture two neutron stars locked in a deadly dance. Over millions of years, their orbits decay until finally they collide. The merger unleashes a shockwave of energy, rippling across the electromagnetic spectrum. Gravitational waves surge outward, and for a fleeting instant, the collision could produce a blistering burst of radio waves, an FRB. This isn't just speculation. In 2017, the LIGO Observatory detected gravitational waves from a neutron-star merger, and while no accompanying FRB was found that time, the door isn't closed. Future observations might catch this cosmic fireworks show in the act. Then there's the birth of a black hole. When a massive star collapses under its own weight, it doesn't always go quietly. Some theorists propose that as a dying star's core implodes, magnetic fields get twisted into knots, snapping like overstretched rubber bands. The result: a shockwave of radio emission an FRB announcing the black hole's arrival to the universe. These one-off bursts could be the death cries of stars, their final moments etched into radio waves traveling across billions of light years. But perhaps the most exotic candidate is the BURSTS, a theoretical zombie pulsar. Imagine a neutron star spinning rapidly, held together by centrifugal force. But if it loses too much energy, it can't support its own weight anymore. In a fraction of a second, it collapses into a black hole, releasing its magnetic field in a catastrophic burst of radiation. The name BURSTS combines the German word for lightning, Blitz, with pulsar, and the effect is just as dramatic, a single, brilliant FRB signaling the star's sudden demise. What's fascinating is how these cataclysms might explain the differences between one-off and repeating FRBs. Collisions and collapses are, by nature, one-time events. But repeating bursts, those could stem from systems with ongoing violence, like a black hole devouring a neutron star piece by piece, or a pulsar caught in a cycle of destruction and rebirth. Each scenario leaves a distinct fingerprint in the bursts we detect. The beauty of these theories is that they don't just solve the FRB puzzle, they open windows into the universe's most extreme environments. Every burst becomes a clue, a fleeting glimpse into the chaotic processes that shape our cosmos. And while we may not have all the answers yet, one thing's certain: the universe is far stranger and far more violent than we ever imagine. This brings us to an even wilder idea, one that pushes the boundaries of physics itself. Could some FRBs be more than just cosmic disasters? Could they be signals of something far more profound, like the universe itself unraveling? That's a story for another moment, but the threads are already weaving together in ways that might redefine our understanding of reality. Now let's take a turn toward one of the most unsettling possibilities in modern physics. What if fast radio bursts aren't just cosmic accidents or alien engineering projects, but something far more fundamental? What if they're the universe itself screaming into the void? This brings us to the universe's death cries theory, where FRBs could be signs of space-time itself unraveling. It sounds like science fiction, but some serious theoretical physicists have explored this idea. The concept ties into one of cosmology's most chilling scenarios, vacuum decay. Here's how it might work. Our universe exists in what physicists call a false vacuum, a seemingly stable but potentially precarious state. Think of it like a marble resting in a shallow bowl. It appears stable, but with enough energy, it could roll into a deeper, truer minimum. If this quantum transition happened somewhere in space, it could create a bubble of true vacuum that expands at nearly the speed of light, rewriting the laws of physics as it spreads. Inside this bubble, atoms might not hold together, chemistry would cease to function, reality as we know it would end. Now here's where FRBs come in. Some researchers suggest that these violent phase transitions in spacetime could generate bursts of energy detectable as radio waves. As the bubble wall between false and true vacuum propagates, it might release concentrated electromagnetic radiation, what we observe as an FRB. Essentially, these bursts would be the first warning signs of cosmic annihilation. The terrifying beauty of this hypothesis is that it aligns with certain properties of FRBs. Their extreme energy fits what models predict for vacuum decay events. Their brief duration matches the timescales of such quantum processes. Even their dispersion, how the signal spreads out, could reflect the way a vacuum decay bubble interacts with the surrounding universe. Of course, this remains speculative. No direct evidence links FRBs to vacuum decay yet, but papers from institutions like Harvard and MIT have explored the mathematical feasibility, showing it's not just wild conjecture. If correct, detecting certain types of FRBs could literally mean we're hearing the first echoes of universal doom. Imagine a scenario where astronomers one day pick up an FRB that fits the vacuum decay profile too perfectly. The implications would be staggering. It would mean the universe isn't just dying slowly through heat death, but actively unraveling in pockets of space, with those destructive bubbles possibly heading our way. Now, before you panic, remember this is still theoretical, but it highlights how FRBs aren't just astronomical oddities. They might be cosmic messengers carrying news about the deepest workings of reality itself. Whether they're alien signals, dying stars, or spacetime's death knell, one thing is clear: when the universe speaks in bursts of radio waves, we should listen closely. Now let's shift our focus to one particular fast radio burst that turned everything we thought we knew upside down. Meet fast radio burst 121102, the first repeating FRB ever discovered. Unlike the one-off bursts that seemed to vanish without a trace, this one kept coming back, defying expectations and forcing scientists to rethink their assumptions. This cosmic repeater was first detected in 2012 by the Arecibo Observatory in Puerto Rico. And what made it extraordinary wasn't just its return performances, but its home, a tiny, turbulent dwarf galaxy nearly 3 billion light-years away. Pinpointing its location was a game-changer. Before this, most astronomers assumed fast radio bursts were cataclysmic events, like neutron star collisions or black hole births, explosions so violent they could only happen once. But fast radio burst 121102 shattered that idea. If a single source could produce multiple bursts, then whatever was creating them had to survive the process, meaning they couldn't be tied to universe-ending disasters. What's even stranger is its behavior. Unlike the predictable ticking of a pulsar, this FRB fires off erratically, sometimes quiet, for months, then suddenly erupting in clusters of bursts within hours. One study even recorded over 160 bursts from it in a single year. The irregularity suggests an engine that's not just persistent, but chaotic, possibly tied to extreme magnetic environments or volatile interactions between dense stellar remnants. The host galaxy adds another layer of intrigue. Dwarf galaxies like this one are often messy, star-forming environments, packed with young, magnetically hyperactive neutron stars called magnetars. Some researchers think fast radio burst 121102 might be tied to one of these cosmic powerhouses, with its bursts triggered by starquakes or magnetic storms. Others speculate it could involve a black hole or some exotic, undiscovered object. Either way, its existence forces us to consider that FRBs might not have a single universal cause. Some could be repeating, others truly one-time events. Perhaps the most thrilling aspect is what fast radio burst 121102 tells us about the diversity of FRBs. If some repeat and others don't, it implies multiple origins, each with its own cosmic story. This repeater alone has spawned dozens of studies, each trying to decode its erratic language. Is it a malfunctioning alien beacon, a magnetar throwing tantrums, or something even weirder? Every burst brings us closer to an answer and further into the mystery. One thing's certain: fast radio burst 121102 isn't just an anomaly. It's a Rosetta Stone for understanding these cosmic signals, proving that when it comes to fast radio bursts, the universe still has plenty of surprises up its sleeve. Now let's talk about the cosmic treasure hunt, how astronomers actually pinpoint where these elusive, fast radio bursts are coming from. It's not as simple as pointing a telescope at the sky and waiting. Capturing an FRB is like trying to photograph lightning with a camera that only snaps a picture every few minutes. The burst lasts milliseconds, and by the time you've registered it, it's already gone. So how do we track something so fleeting? The answer lies in a game-changing technique called interferometry. Imagine you're trying to find the source of a sound in a crowded room. If you have just one ear, it's tough, but with two ears, you can triangulate the direction. Interferometry works the same way, but instead of ears, we use multiple radio telescopes spread across vast distances. By combining their signals, astronomers can achieve incredibly precise localization. This is where telescopes like the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, come in. Unlike traditional dishes, CHIME is a stationary array of cylindrical antennas with no moving parts. It scans the entire northern sky every day, making it a relentless FRB hunter. The real breakthrough came in 2020, when astronomers detected something unprecedented, a fast radio burst originating right inside our own Milky Way. This wasn't some distant, enigmatic signal from billions of light years away. This one was homegrown, traced to a known magnetar called SGR 1935+2154. The discovery was monumental because it gave scientists a front-row seat to study an FRB's engine up close. The magnetar's outburst matched the properties of more distant FRBs, strongly suggesting that at least some of these cosmic flashes come from highly magnetized neutron stars. But here's where it gets even more fascinating. When we map the sky distribution of FRBs, they're not scattered randomly. They cluster in ways that hint at the large-scale structure of the universe. Some are linked to massive galaxies, others to tiny dwarfs like the host of fast radio, BURST 121102. These host galaxies are like crime scenes, offering clues about the environments that spawn FRBs. For instance, repeating FRBs often come from young, turbulent galaxies with lots of star formation, while one-off bursts might prefer quieter neighborhoods. This cosmic cartography isn't just about curiosity, though. By tracing FRBs through space, astronomers are solving another mystery, the missing baryon problem. You see, most of the universe's ordinary matter isn't in stars or galaxies. It's in diffuse gas between them, so thin it's nearly invisible. But when an FRB's signal travels through this plasma, it slows down slightly, leaving a fingerprint called dispersion. By measuring this, scientists can map the universe's hidden matter like never before. So every time we localize an FRB, we're not just answering one question. We're peeling back layers of the cosmos, unlocking secrets about magnetic fields, galaxy evolution, and even the fabric of space itself. And with next-gen telescopes coming online, this treasure hunt is only getting started. Now here's something that will bend your mind. Fast radio bursts aren't just mysterious signals. They're cosmic detectives helping solve one of astronomy's biggest cases, the missing baryon problem. Picture this: when scientists added up all the visible matter in the universe, stars, galaxies, gas, they hit a snag. The numbers didn't match. Nearly half of the ordinary matter predicted by theory was simply gone. We're not talking dark matter here, but regular atoms that seem to have vanished without a trace. The breakthrough came when researchers realized FRBs could act like interstellar flashlights. As these bursts race across the cosmos, their signals pass through clouds of ionized gas plasma so thin it's practically invisible to telescopes. But here's the magic. The lower frequencies of the FRB slow down slightly in this plasma, creating a delay called dispersion. The more material the signal travels through, the greater this smear effect becomes. By measuring this dispersion, astronomers can essentially weigh the invisible matter between galaxies, like counting tree rings to measure a forest's age. Let's break this down further. Think of the universe's structure as a gigantic spiderweb, the cosmic web, with galaxies clustered along its shimmering threads. Between these threads lie enormous voids filled with wispy filaments of gas. This is where the missing baryons have been hiding, too diffuse to emit light, but dense enough to leave fingerprints on passing FRBs. In 2018, a study using fast radio burst 180924 proved it. The burst's dispersion revealed more baryons in intergalactic space than all stars and galaxies combined, finally accounting for the universe's missing atoms. What makes this even more powerful is how FRBs map space in 3 dimensions. Unlike traditional methods that measure gas in a single line of sight, multiple FRBs crisscrossing different regions let scientists reconstruct the cosmic web's full architecture. It's like using a handful of scattered fireflies to trace the outline of an invisible maze. Recent observations show this web isn't uniform. Some areas are knotty with clusters, others eerily empty, matching supercomputer simulations of the universe's growth. But the story doesn't end there. The dispersion measurements also reveal turbulence in these hidden plasma rivers, hinting at violent events like ancient supernova shockwaves or jets from supermassive black holes that stirred the cosmic soup over billions of years. Every new FRB detected adds another data point, sharpening our view of this shadowy scaffolding that shapes the universe. So next time you hear about a fast radio burst, remember, it's more than a cosmic oddity. It's a beacon illuminating the darkest corners of space, helping us solve mysteries we didn't even know how to approach a decade ago. And as telescopes grow more sensitive, these fleeting flashes might just reveal how the universe threads itself together, one burst at a time. Now, let's shift gears to another fascinating clue hidden in these signals: the way their light twists and turns, revealing extreme cosmic environments unlike anything in our solar system. Polarization, as we'll see next, opens a whole new window into the magnetic chaos where FRBs are born. Here's the next part of the script. Now, let's peel back another layer of the fast radio burst mystery, one that involves light behaving in strange, twisted ways. Imagine a beam of light not just flashing through space, but doing so with a distinct spin or alignment, like a dancer twirling in a cosmic ballet. This phenomenon is called polarization, and it's giving scientists crucial clues about the extreme environments where FRBs originate. Take fast radio burst 2019-0520b, detected in 2022. Its light wasn't just bright, it was highly polarized, meaning its waves were vibrating in a specific direction. But here's where it gets wild. Some FRBs show linear polarization, where the light waves align in a straight path, while others exhibit circular polarization, spiraling like a corkscrew. These differences aren't just aesthetic, they're fingerprints of the magnetic chaos these bursts endure on their journey to us. Linear polarization often points to a brutal trip through dense magnetic fields. Think of it like a flashlight beam passing through a storm of cosmic needles. The light gets combed into a single plane. This suggests the FRB passed near something like a supermassive black hole or a neutron star with a magnetic field trillions of times stronger than Earth's. In contrast, circular polarization hints at turbulence, with magnetic fields twisting the light like a taffy pull. Some researchers argue this could mean the burst originated inside a thick nebula of magnetized particles, or even a debris field from a recent stellar explosion. But polarization doesn't just reveal the neighborhood, it also challenges our theories. For example, if an FRB's polarization changes over time, it might mean the source itself is rotating, like a lighthouse beam sweeping across our line of sight. That's a big deal because it could rule out one-time cataclysms, like colliding stars, and point instead to objects that persist, like magnetars. The most extreme cases show Faraday rotation, a fancy term for when polarized light gets its direction scrambled by magnetic plasma. Fast radio burst 2019 0520b had this in spades, requiring a magnetic environment so intense it's unlike anything in our galaxy. Some theorists suggest this could mean the burst came from a region near the edge of a black hole's accretion disk, where space itself is twisted into knots. So why does this matter? Because polarization is like a cosmic weather report, telling us about the storms these signals endured. And with every new polarized FRB, we're piecing together a map of the universe's most violent magnetic hotspots, places where the laws of physics get stretched to their limits. Up next, we'll see how a radical new telescope is turning this trickle of FRB data into a flood, revolutionizing our hunt for these enigmatic signals. Now, let's turn our attention to a game-changer in the hunt for fast radio bursts, a telescope so revolutionary. It's turning whispers from the cosmos into a chorus. Nestled in the mountains of British Columbia, Canada's CHIME telescope isn't your typical astronomical instrument. Forget massive rotating dishes or delicate mirrors, this one looks more like a futuristic half-pipe, with 4 towering cylindrical arrays stretching the length of a football field. And here's the kicker, it doesn't move an inch. CHIME's stationary design is its superpower. While traditional telescopes pivot to track celestial objects, CHIME lets the Earth's rotation do the work. Its arrays act like a giant cosmic net, catching radio waves as they sweep across the sky. But the real magic happens in how it processes data. Every second, CHIME drowns in a deluge of radio noise cell signals, satellite chatter, even microwave ovens. Sifting through this chaos to find FRBs is like spotting a needle in a galaxy-sized haystack. That's where artificial intelligence steps in. Machine learning algorithms scour CHIME data in real time, flagging potential FRBs with inhuman speed. These AI tools learn from past detections, growing sharper with each burst they analyze. The result: CHIME has bagged thousands of FRBs since its 2018 debut, including rare repeaters and bizarre one-offs. It's as if we've upgraded from a magnifying glass to a floodlight in our search for these cosmic enigmas. What sets CHIME apart isn't just its volume of discoveries, it's the telescope's ability to map the entire northern sky daily. While older facilities might stumble upon an FRB by chance, CHIME methodically scans vast swaths of space, turning sporadic detections into a steady stream. This shift from scarcity to abundance is rewriting the FRB playbook. Suddenly, we're not just studying individual bursts, we're comparing populations, spotting patterns, and even catching some FRBs in the act of repeating. One of CHIME's standout moments came in 2020, when it detected a fast radio burst erupting from a magnetar within our own galaxy, the first such event with a confirmed local origin. This was the smoking gun linking at least some FRBs to these highly magnetic stellar corpses. But CHIME data also raises new puzzles. Why do some bursts arrive in clusters? Could there be multiple cosmic factories producing different flavors of FRBs? As we marvel at CHIME cylindrical arrays silently harvesting the universe's radio whispers, one thing is clear: we're no longer just chasing ghosts in the cosmic static. We're building a catalog of these elusive signals, each one a breadcrumb leading us deeper into the mysteries of magnetic monsters, intergalactic plasma, and perhaps, just perhaps, something even stranger. Now, just when we thought fast radio bursts couldn't get any more puzzling, nature, and sometimes our own kitchen appliances, decide to play tricks on scientists. Enter the world of puritans, those mischievous cosmic imposters that had astronomers scratching their heads for years. At first glance, these signals looked almost identical to FRBs, same fleeting bursts, same dispersive sweep across radio frequencies. But there was one glaring difference. Puritans weren't coming from deep space, they were coming from Earth. The big reveal happened back in 2015, when researchers at Australia's Parkes Observatory noticed something odd. These Puritans kept appearing during workday hours, never at night or on weekends. Suspicious, right? After months of detective work, they cracked the case. The culprit, a microwave oven in the observatory's staff lunchroom. Here's how it worked. When someone opened the microwave door mid-cycle, the escaping radiation created a burst that mimicked an FRB's signature. The telescope, ever the eager listener, picked it up as a cosmic event. It's like mistaking your neighbor's rogue Wi-Fi signal for a message from aliens. What makes Puritans so sneaky is their dispersion effect, which initially mirrored the way real FRBs stretch out as they travel through space. But unlike genuine cosmic bursts, Puritans showed a telltale quirk: their dispersion only appeared in certain directions, a dead giveaway they were local. Scientists eventually distinguished them by their smudged spectrograms compared to FRBs' cleaner frequency patterns. This mix-up wasn't just a funny blunder, it taught astronomers a valuable lesson. The hunt for FRBs requires more than cutting-edge telescopes. It demands cosmic detective skills to separate deep space whispers from earthly noise. Modern observatories now use multi-location verification. If a signal appears at Parkes but not at telescopes in Chile or Hawaii, it's likely a Puritan, not an FRB. The Puritan saga also highlights how far we've come. Early FRB discoveries were treated with skepticism, partly because of these false alarms. Today, armed with better tools and humor about microwaves, astronomers can focus on the real enigmas lighting up our universe, one fleeting burst at a time. Now, shifting our gaze from cosmic imposters to cosmic measuring tapes, let's talk about how fast radio bursts might just hold the key to solving one of astronomy's biggest headaches, the Hubble tension. This isn't just about detecting mysterious signals anymore. It's about using them as the universe's own rulers to measure how fast everything is flying apart. Here's the puzzle astronomers are wrestling with. For decades, we've had two main ways to calculate how quickly the universe is expanding, a number called the Hubble constant. One method looks at nearby galaxies and their Doppler-shifted light, while the other studies the afterglow of the Big Bang, the cosmic microwave background. The problem: these two methods give slightly different answers, like two clocks ticking at mismatched speeds. That discrepancy has sparked what scientists call the crisis in cosmology, because it might mean there's something fundamental we're missing about how the universe works. Enter fast radio bursts, the universe's accidental measuring sticks. When an FRB travels across space, its signal gets stretched out by all the electrons it passes through, a phenomenon called dispersion. But here's the clever part. By measuring that dispersion and knowing the FRB's distance, thanks to its host galaxy, astronomers can calculate how much stuff, mostly ionized gas, lies between us and the burst. This gives us a snapshot of the universe's missing matter, the invisible scaffolding that makes up the cosmic web. But FRBs don't stop there. Because they're so bright and short-lived, they also let scientists track the universe's expansion directly. Think of it like this. If an FRB's host galaxy is moving away from us due to cosmic expansion, the burst signals will be redshifted, stretched to longer wavelengths. By comparing that redshift with the galaxy's distance, we get an independent measure of the Hubble constant. Early studies, like those using the repeating FRB 121102, suggest these bursts could bridge the gap between the two conflicting methods. The real game changer, FRBs are everywhere. Billions must occur daily across the sky, and each one is a potential data point. As telescopes like Canada's CHIME detect more of them, we're building a vast, three-dimensional map of cosmic expansion. Unlike traditional methods that rely on painstakingly measuring individual stars or galaxies, FRBs offer a fast, precise way to sample the universe's stretching fabric. So could FRBs end the Hubble tension? It's too soon to say, but they're already shaking up cosmology. By acting as neutral referees, these bursts might reveal whether the tension is due to measurement errors, unknown physics, or something even wilder, like dark energy evolving over time. Whatever the answer, one thing's clear. Fast radio bursts aren't just cosmic mysteries anymore. They're turning into the universe's most unexpected tools, helping us measure the immeasurable. But before we can fully trust fast radio bursts as cosmic yardsticks, we need to crack their greatest mystery: what's actually powering these ultra-energetic flashes in the first place. The truth is, we're staring at a cosmic crime scene with multiple suspects, and each one leaves behind wildly different clues. At the top of the list, Magnetars, the universe's ultimate powerhouses. These neutron stars with magnetic fields 1,000 trillion times stronger than Earth's occasionally snap under the strain, releasing starquakes or magnetic reconnection events. Picture a rubber band stretched too far. When it finally breaks, all that pent-up energy explodes outward in a magnetar flare. The math checks out too. The energy released during these violent episodes neatly matches what we've measured from some fast radio bursts, especially the Milky Way's own FRB 2020, which was traced back to a hyperactive magnetar named SGR 1935 plus 2154. But here's where it gets complicated. Not all FRBs fit the magnetar profile. Some seem to erupt from calmer neighborhoods where magnetars shouldn't exist. That's led astronomers to consider a second culprit: asteroids smashing into neutron stars. Imagine a mountain-sized space rock plunging into a dense stellar corpse at half the speed of light. The impact would vaporize instantly, creating a superheated plasma bubble that detonates as a radio burst. It's an elegant solution, especially for one-off FRBs, but there's a catch. The math says we'd need an implausible number of asteroids making BURSTs hits to explain all the bursts we detect. This brings us to the wildcard theories, the ones that flirt with the edges of known physics. Take cosmic strings, hypothetical flaws in spacetime left over from the Big Bang. If these ultra-dense threads snap or kink, they could unleash gravitational tsunamis capable of birthing FRBs. Even stranger are proposals involving black hole fireworks or neutron stars collapsing into quark stars, events so violent they temporarily warp the laws of physics. The real head-scratcher: some FRBs pack energies that defy conventional explanations. Take FRB 181214, which released more energy in a millisecond than our Sun does in 3 days. To produce that, you'd need an engine 100% efficient, something impossible under current physics, where even the mightiest cosmic events waste energy as heat or light. This has forced scientists to reconsider fundamental assumptions. Could FRBs be tapping into dark matter, harnessing extra dimensions? For now, these ideas remain in the realm of cool but unproven. What's certain is this fast radio bursts aren't just one thing. They might be cosmic car crashes, stellar heart attacks, and spacetime earthquakes all rolled into one. And as we gather more data, we're not just solving an astrophysical whodunit. We're stress-testing the very laws that govern reality. Now, let's step back for a moment and revisit one of astronomy's most infamous mysteries, the WOW signal, detected in 1977 by Ohio State University's Big Ear radio telescope. This 72-second burst of radio waves was so startling that astronomer Jerry Amon circled it on the printout and scribbled, "Wow." Next to it, decades later, we're still asking the same question. Was this a cosmic fluke or an intentional hello from another civilization? And here's where things get eerily familiar. Fast radio bursts and the WOW signal share an uncanny resemblance, brief, unexplained, and packing enough intrigue to fuel endless debates. First, the similarities. Both signals appeared out of nowhere, vanished just as quickly, and have resisted definitive explanation ever since. The WOW signal was narrowband, meaning it was concentrated at one specific frequency, a hallmark of artificial transmission. Fast radio bursts, on the other hand, are broadband, sweeping across frequencies like a cosmic slide whistle. But here's the kicker. Both signals originated from regions of space devoid of obvious natural sources. The WOW signal came from the constellation Sagittarius, while many FRBs trace back to distant galaxies with no visible cataclysmic events. So, could they both be cosmic SOS signals? Not so fast. Skeptics argue that nature has a flair for mimicking intelligence. Consider pulsars. When first discovered in 1967, their precise radio pulses had astronomers briefly considering the possibility of alien beacons. Today, we know them as spinning neutron stars. The WOW signal could easily be a similar case, a natural phenomenon we just haven't identified yet. Some propose it was a hydrogen cloud drifting in front of a star, amplifying its radio emissions. Others blame passing comets, though that theory's been largely debunked. Where FRBs complicate the debate is their sheer variety. The WOW signal was a one-off, but fast radio bursts include repeaters and one-shots, each with different energy profiles and host environments. If some FRBs are natural and others artificial, how do we tell the difference? The answer might lie in their fingerprints. Artificial signals, like earthly radio stations, would have telltale patterns, narrowband frequencies, or deliberate repetition. The WOW signal's narrowband nature still makes it a prime candidate, whereas FRB's broadband sweeps lean natural. But let's not dismiss the cosmic coincidence factor. Both signals emerged from radio astronomy's blind spots. The WOW signal was detected at 1420 MHz, a frequency shielded by international agreement to avoid terrestrial interference, making it a quiet channel ideal for interstellar eavesdropping. Similarly, FRBs were only discovered when radio telescopes became sensitive enough to catch millisecond blips. It's as if the universe waited for us to develop the right tools before sending its memos. So where does this leave us? The WOW signal and FRBs might be two sides of the same coin, cosmic phenomena we're only beginning to decode. Whether they're natural oddities or extraterrestrial postcards, one thing's certain: they remind us that the universe is far stranger and perhaps far noisier than we ever imagined. And with every new signal, we're not just listening to space, we're learning how to hear it. Now, let's take a detour from the science and step into the realm of imagination, because fast radio bursts haven't just captured the attention of astronomers. They've also sparked the creativity of storytellers, filmmakers, and artists, weaving their way into pop culture as modern-day cosmic mysteries. It's no surprise that FRBs have become a favorite plot device in science fiction. After all, what's more tantalizing than an unexplained signal from deep space? Take the classic film Contact, for example. While it predates the discovery of FRBs, its portrayal of a repetitive alien transmission, complete with prime numbers, mirrors the intrigue surrounding repeating fast radio bursts. The idea that these signals could be a deliberate message, a cosmic handshake, is a theme that resonates deeply with our curiosity about who else might be out there. Netflix's documentary Unknown, Cosmic Time Machine also brought FRBs into the spotlight, blending cutting-edge science with cinematic storytelling. The film explores how these bursts challenge our understanding of the universe, framing them as cosmic puzzles waiting to be solved. And then there's literature. Novels like The Three-Body Problem by Liu Cixin dabble in similar territory, imagining advanced civilizations using cosmic phenomena to communicate across the void. But pop culture doesn't just borrow from the mystery of FRBs, it amplifies it. Think about how these bursts are often depicted as shimmering, otherworldly pulses on a scientist's screen, or as the catalyst for first contact in a sci-fi blockbuster. These fictional portrayals shape how the public perceives real-life FRBs, turning them into symbols of humanity's thirst for discovery. Sometimes, they even inspire real science. The WOW signal itself became legendary partly because of how it was mythologized in books and documentaries, and FRBs are following the same path. Yet, there's a fascinating tension here. While science fiction loves to leap to extraterrestrial explanations, scientists urge caution, reminding us that nature is often stranger than fiction. The same cosmic phenomena that fuel alien conspiracy theories in movies are, in reality, more likely to be neutron stars or colliding black holes, but that doesn't make them any less thrilling. If anything, the fact that reality can rival the wildest sci-fi plots is a testament to how incredible our universe truly is. So the next time you watch a movie or read a book where a mysterious signal from space sets the story in motion, remember, the real-life version might be even weirder. And as we keep unraveling the secrets of fast radio bursts, who knows? The truth could end up being stranger than anything Hollywood has dreamed up. Now, let's shift our gaze from the silver screen to the cutting-edge tools that might finally unlock the secrets of fast radio bursts. Because while pop culture spins tales of alien messages, scientists are hard at work designing the next generation of telescopes, instruments so powerful they could rewrite our understanding of the cosmos. At the forefront of this quest is the Square Kilometre Array, or SKA, set to be the world's largest radio telescope when it's fully operational. Imagine a network of thousands of antennas stretching across South Africa and Australia, working in unison to scan the sky with unprecedented sensitivity. The SKA won't just detect FRBs, it'll pinpoint their locations with pinpoint accuracy, allowing us to trace these bursts back to their host galaxies like cosmic detectives. And here's the kicker. It's expected to catch dozens of FRBs every single day, giving researchers a treasure trove of data to analyze. But the SKA isn't alone in this hunt. Upgrades to the Atacama Large Millimeter Array, or ALMA, are set to supercharge its ability to study FRBs in millimeter wavelengths. This could reveal new clues about the environments these bursts originate from, whether it's the chaotic magnetic fields around magnetars or something even more exotic. Together, these telescopes form a dream team, covering everything from radio waves to infrared, painting a fuller picture of FRBs than we've ever had before. What's even more exciting is the push to catch FRBs in real time using multi-messenger astronomy. Picture this: the moment a burst is detected, telescopes around the world, and even in space, swing into action, scanning the same patch of sky for gravitational waves, neutrinos, or gamma rays. It's like turning the entire planet into one giant cosmic observatory. Already, projects like the Zwicky Transient Facility are syncing up with radio telescopes to chase these fleeting signals, hoping to catch an FRB's afterglow or a coinciding explosion. The stakes couldn't be higher. If we can link an FRB to a gravitational wave event, for instance, it might confirm whether colliding neutron stars are truly behind some of these bursts. Or if we spot a neutrino counterpart, it could hint at processes involving black holes or other extreme objects. Every piece of the puzzle brings us closer to answering the big question: are these bursts nature's fireworks, or something even more extraordinary? So while Hollywood imagines FRBs as interstellar SOS signals, the real drama is unfolding in control rooms and data centers, where scientists are building the tools to listen and finally understand what the universe is trying to tell us. And with every upgrade, every new telescope coming online, we're not just chasing bursts, we're chasing the truth. Now, let's dive into one of the most puzzling twists in the fast radio burst mystery, the so-called dark FRBs. These bursts don't just challenge our understanding of their origins, they defy it entirely by leaving no trace in other wavelengths of light. Imagine hearing a thunderclap but seeing no lightning. That's the enigma scientists are grappling with when it comes to these elusive signals. Most FRBs, as wild as they are, come with some breadcrumbs like a host galaxy visible in optical or infrared telescopes, or an accompanying flare from a magnetar. But dark FRBs, nothing. No afterglow, no visible source, no hint of where they came from. It's as if the universe is playing a cosmic game of hide and seek, and we're left squinting into the void. So what could possibly produce such a stealthy burst of energy? One theory points to primordial black holes, hypothetical remnants from the universe's earliest moments. These aren't your typical black holes formed from collapsing stars. They're thought to be far smaller, some no heavier than an asteroid, yet packing the same gravitational punch. If one of these ancient objects were to evaporate or collide, it might unleash an FRB without the usual electromagnetic fanfare. The catch: we've never definitively detected a primordial black hole, making this idea as tantalizing as it is speculative. Then there's the quark star hypothesis. Picture a neutron star, but under such immense pressure that its neutrons break apart into their fundamental components, quarks. The result: an ultra-dense object even stranger than a magnetar, possibly capable of generating FRBs through quantum-scale fireworks we can't yet imagine. Some models suggest quark stars could produce bursts without the telltale X-ray or gamma-ray signatures, neatly explaining the dark in dark FRBs. But like primordial black holes, quark stars remain theoretical, for now. And let's not overlook dark matter. Could these invisible particles, which make up most of the universe's mass, be somehow involved, perhaps dark matter clumps interacting in ways we don't yet understand could spark these bursts. It's a long shot, but in a mystery this deep, every possibility deserves a look. The absence of light might actually be the biggest clue. If dark FRBs truly originate in environments devoid of conventional matter, they could be probing realms of physics currently beyond our reach. Each one we detect is like a message in a bottle from a shadowy corner of the cosmos, one we're only beginning to decode. So while telescopes like the SKA and ALMA hunt for FRBs we can see, the real revolution might come from the ones we can't. Dark FRBs don't just add another layer to the mystery, they could rewrite the rules entirely, and that's what makes them so thrilling, because in the end, the universe's quietest signals might be the ones that speak the loudest. Now, let's venture into one of the most mind-bending ideas, yet could fast radio bursts be messages from the future? It sounds like sci-fi, but some physicists have seriously entertained the possibility that FRBs might be echoes of civilizations yet to come. Imagine a signal not just from across space, but across time itself. The idea hinges on a quirky aspect of physics known as retrocausality, where effects can precede their causes. In quantum mechanics, particles can exhibit behaviors that seem to defy linear time, leading some theorists to speculate that information might travel backward through time under extreme conditions. If that's true, an advanced civilization billions of years ahead of us might find a way to encode signals into the fabric of spacetime, sending them back to us as FRBs. One provocative paper on the RZIV preprint server suggested that if a future civilization harnessed the energy of a collapsing black hole or a cosmic string objects with unimaginable gravitational power, they could manipulate spacetime to transmit signals into the past. The dispersion patterns of some FRBs, with their precise frequency sweeps, have even been floated as potential signatures of artificial encoding. But before we start drafting replies to our descendants, let's pump the brakes. The biggest hole in this theory: causality. The laws of physics, as we understand them, don't just prevent time travel, they guard against paradoxes that would unravel reality itself. If FRBs were messages from the future, they'd require a mechanism to bypass entropy, quantum decoherence, and a host of other cosmic roadblocks. Even Hawking's chronology protection conjecture posits that the universe has a built-in no-time travel policy to prevent such chaos. Then there's the practical issue of energy. To send a signal backward in time, you'd need to concentrate more energy than a supernova, something no known technology, even theoretically, could achieve. And if a future civilization had that capability, why send a millisecond burst? Why not a clearer, sustained message? Still, the fact that scientists are willing to explore such wild ideas shows just how baffling FRBs remain. Whether they are natural or engineered, these bursts push us to question not just what's out there, but when. And that's the beauty of the mystery. It's not just about decoding the universe's secrets, but wondering whether some of those secrets haven't even happened yet. Now, let's shift gears to a debate that's as gripping as it is unsettling. Should we even consider replying to fast radio bursts if there's a chance they're alien signals? This isn't just science fiction. The question touches on real ethical dilemmas that scientists and philosophers have wrestled with for decades. Picture this: we detect an FRB that seems too structured to be natural. Do we risk answering? The dark forest hypothesis, popularized by sci-fi but taken seriously in some academic circles, paints a chilling picture. It suggests the universe might be like a dark forest where every civilization stays silent to avoid being hunted by predators. If that's true, broadcasting our location could be catastrophically naive. Advocates of this idea argue that advanced civilizations might see newcomers as threats or resources. History on Earth, after all, isn't kind to societies that encounter more powerful outsiders. On the other side of the debate are groups like METI, messaging extraterrestrial intelligence, who actively send signals into space. They argue that hiding is pointless. Any civilization advanced enough to detect FRBs likely already knows we're here. Plus, they say, collaboration could leapfrog our technology and understanding of the cosmos. But critics fire back. METI efforts, like the 2017 transmission to a nearby star system, are akin to shouting into a jungle without knowing what's listening. Even Stephen Hawking warned that contacting aliens could be as risky as Columbus landing in the Americas. It didn't turn out well for the Native Americans. The stakes are dizzying. A reply could invite friendship or invasion. Some scientists propose middle ground solutions, like establishing international protocols for responding. Others suggest sending coded math or physics concepts as a universal handshake, avoiding details about Earth's location. But here's the catch: even a safe signal could reveal our presence. Radio waves travel at light speed, so a reply would take years to reach its target. But once sent, there's no taking it back. Then there's the legal gray area. No laws govern interstellar communication, leaving the decision to a handful of researchers with radio telescopes. In 2010, a team in Ukraine beamed a message to Gliese 581, a star with potential planets, without public consent. Should such power rest with individuals, or does humanity deserve a vote? The debate boils down to a single, haunting question. In a universe where we know so little, is curiosity worth the risk? Whether FRBs are cosmic accidents or deliberate signals, the act of replying forces us to confront not just who might be out there, but who we are, and how much we're willing to gamble on the unknown. Now, let's take a leap into one of the wildest and most mind-bending theories about fast radio bursts. What if these mysterious signals aren't just coming from distant galaxies or alien civilizations, but from entirely different universes? It sounds like science fiction, but some physicists are seriously considering whether FRBs could be tied to quantum entanglement, or even flashes from parallel realities. Here's how the fringe theory works. Quantum entanglement, often called spooky action at a distance by Einstein, is the bizarre phenomenon where two particles become linked, so that changing one instantly affects the other, no matter how far apart they are. Now, imagine if FRBs aren't just bursts of radio waves, but echoes of quantum activity on a cosmic scale. Some researchers speculate that if entanglement operates across vast distances, it might produce detectable signals, like FRBs, when entangled particles in different parts of the universe interact. Even more speculative is the idea that FRBs could be entanglement flashes from parallel universes in a multiverse. The concept hinges on theories like string theory or the many worlds interpretation, which suggest our universe is just one bubble in an infinite cosmic foam of realities. If another universe brushed against ours, even briefly, the collision might release a burst of energy detectable as an FRB. It's a stretch, but not impossible. In fact, a few papers on RZIV, the repository for cutting-edge physics research, have toyed with this idea, suggesting that some FRBs might carry signatures of higher dimensional physics. Of course, critics are quick to point out the holes in these theories. For one, we have no direct evidence that parallel universes exist, let alone that they'd produce radio bursts. And while quantum entanglement is real, scaling it up to cosmic proportions is a whole other challenge. The energy required to create an FRB through entanglement would be staggering, far beyond anything we've observed in labs. Plus, FRBs follow patterns that so far align better with astrophysical objects like magnetars than with multiverse collisions. But here's why the idea lingers. FRBs are still so poorly understood that they leave room for bold speculation. If even a tiny fraction of these bursts defy conventional explanations, could they be our first glimpse into quantum weirdness on a universal scale? Or might they hint at realities beyond our own? It's a long shot, but in a field where mysteries outnumber answers, sometimes the wildest ideas push science forward. After all, many of history's biggest breakthroughs started as fringe theories. So while we might not be hearing from alternate versions of ourselves just yet, the possibility alone stretches our imagination, and maybe, one day, our understanding of the cosmos. Turning from the edges of theoretical physics back to the concrete mysteries, fast radio bursts continue to defy easy explanations. Even after decades of study, three core questions haunt researchers, each more puzzling than the last. First, the enigma of repetition. Why do some FRBs fire a single, fleeting signal, while others, like the famous repeater FRB 121102, blast out repeated pulses for years? The leading magnetar theory struggles here. Starquakes or magnetic flares might explain one-off bursts, but repeating FRBs suggest a stable engine, something that can fire again and again without destroying itself. Some propose exotic scenarios, like a neutron star orbited by an asteroid belt, each collision sparking a new burst. Others wonder if repeaters are tapping into an unknown energy reservoir, perhaps through quantum phenomena we haven't yet imagined. Then there's the energy problem. The most powerful FRBs, like the record-breaking FRB 20,220,610, detected in 2022, release more energy in a millisecond than our Sun does in 3 decades. What cosmic powerhouse can do that? Even hyper-magnetized neutron stars might not be enough. This has led to wilder proposals. Could some FRBs come from the annihilation of primordial black holes, theoretical leftovers from the Big Bang? Or are we seeing the collapse of cosmic strings, hypothetical defects in spacetime itself? The sheer scale pushes astrophysics to its limits, hinting that either our models are incomplete or we're witnessing entirely new physics. And lurking beneath it all is perhaps the biggest question: are we missing whole categories of FRBs? Current telescopes are biased toward detecting bright, high-frequency bursts, but what if fainter, slower, or differently polarized signals exist, hiding in plain sight? The CHIME telescope's recent discovery of ultra-long FRBs lasting seconds instead of milliseconds suggests we've only scratched the surface. Upcoming missions like the Square Kilometre Array, with unprecedented sensitivity, could unveil a hidden zoo of FRB varieties, each carrying clues about their origins. The race for answers is accelerating. Later this year, NASA X-ray Polarimetry Explorer will study magnetar flares in tandem with radio telescopes, hunting for direct links to FRBs. Meanwhile, projects like DSA 2000 aim to localize thousands more bursts, mapping their cosmic neighborhoods. Every new detection chips away at the mystery, inching us closer to knowing whether these are alien signals, stellar catastrophes, or something even stranger. The universe, it seems, still has a few cards left to play. So where does that leave us in this grand cosmic puzzle? After diving into the depths of fast radio bursts, one thing is clear: whether they're engineered signals from distant civilizations or the death cries of collapsing stars, FRBs are rewriting the rules of astrophysics. They're like cosmic Rosetta Stones, holding keys to mysteries we're only beginning to crack. On one side, the alien hypothesis tantalizes with possibilities. The idea that advanced beings might be beaming signals across the cosmos captures our imagination, echoes of science, fiction turned potential reality. But science demands evidence, and so far, no repeating patterns or decipherable messages have emerged. The lighthouse model of extraterrestrial beacons remains speculative, overshadowed by the sheer variety of FRB behaviors. Meanwhile, natural explanations keep gaining ground. Magnetars, neutron star collisions, even the decay of space-time itself. Each theory offers compelling pieces of the puzzle. Yet none fully explains every facet of FRBs. The repeating bursts, the staggering energies, the odd outliers like ultra-long FRBs. They all hint that our current models are incomplete. Perhaps the truth lies in a mix of phenomena or something entirely unforeseen. What's undeniable is how FRBs are transforming astronomy. They've become tools for probing the universe's hidden structures, mapping the cosmic web's missing matter, and even measuring the expansion of space itself. Every new detection, whether from CHIME or the upcoming square-kilometer array, peels back another layer of this enigma. So is the universe shouting at us or whispering secrets we're just learning to hear. Either way, FRBs remind us how much remains unknown. They're an invitation to stay curious, to keep questioning, and to marvel at the fact that even in an age of advanced telescopes, the cosmos can still surprise us. If you're as captivated by these mysteries as we are, don't miss out on the next chapter. Hit subscribe and tap that notification bell because the story of fast radio bursts is far from over. Who knows, the next big discovery might be just one burst away.